Hello, this is Roberto and this is the HVAC is my channel. Today we're going to be talking about foreground reflectance for windows for heat load calculations, aka Albedo. Alright, so let's get into it. So this is a very important concept because this is going to increase or reduce our overall heat load, because we know, as we saw in the previous video in the heat load calculations for fenestration, what we have is that the windows present a very high amount of heat loss or heat gain. So that's why it's important. Okay, so let's talk about, or let's start with the definition. We're gonna put that as green. Okay, so albedo, okay, albedo. So this is represented by the Greek word rho, and we're gonna put in here a G because we're gonna be talking about the ground. Okay, so what is actually albedo? So albedo is a fraction, and we're gonna put that in yellow. Like, let's put in yellow. So it's a fraction. Let's put in here fraction. Okay, it's a fraction of the sunlight. But when we talk about sunlight, there are different terms. For example, we have incident, reflected, transmitted, absorbed, and everything comes with radiation. So in this case, we will talk about incident sunlight radiation. Okay, so let's put incident, and we're going to explain that in a few. Incident, okay, it's a fraction of the incident sunlight. Okay, sunlight, okay, sunlight that is reflected. Okay, that is reflected. But since we're talking about G, is reflected from the ground. Okay, from the ground. In different softwares for heat load calculation, what they call is, for example, foreground reflectance. Okay, foreground reflectance. And the example on the right is from RightSoft. So I took a screenshot from RightSoft, and we're gonna put that in pink. So in pink, what we have is the properties of the window. See, construction type, low E. We're also gonna be talking about emissivity, the orientation, the height, see, the area. But most importantly, there is one part that says foreground. That's related to the foreground reflectance, and that depends on the ground itself. So you can have a default 0.20, you can have new concrete, you can have tar and gravel. As you can see in here, there is less reflectance, 14% on tar and gravel, and we have more reflectance when you have a new concrete, 32%, for example. Okay, so if you're doing a heat load calculations, you can consider this as putting as 0.2, but if you are doing a worst case scenario, for example, see, you can increase the heat load by selecting new concrete. New concrete is 0.32. If you want to be more conservative, for example, if you want to size your system, you're going to have a 2-ton unit, or maybe a 1.5. But if you do all your windows, you put in new concrete, 0.32 more reflectance, then your load is going to increase, which is, instead of a 2-ton unit, you're going to have possibly a 2.3 ton unit, so you can round it up to 2.5. So you're being more conservative, more careful. And if you do less, then you're reducing your heat load. However, you can leave it in default, but in worst case scenarios, if you want to be conservative, put it in new concrete 0.2. Okay, so now that we know that, so we're gonna make a graph in here for albedo. So this is depending on the ground. So if we have the ground in here, let's put in here the ground. Mainly, you need to know what type of ground you're talking about. You can have new concrete, you can have green grass. So typically for grass, it's 0.23. As usual, the default, they put it as 0.0. So no, 0.2. Now in here, so if you have the sun, okay, so this is gonna have a ray, right? Here we go, the ray. And that's what we call incident. Okay, we're gonna put it here, incident. incident, okay? Incident radiation or ray, sunlight, and then one part actually is going to be transmitted. Let's put in here transmitted. Okay, transmitted. Okay, and the other part is going to be absorbed by the heat, by the ground. Absorbed. See, we're going to put in here absorbed. And what we need to know, we're going to put this in pink. So let's put that. This is most importantly. See, this is reflected. That's going to be reflected. Okay. So if that's the case, let's continue with the window. That's going to be reflected to the window. So the window is going to be right here. See, the window. Okay. So it's directly reflected to the window, and that's what we call albedo. All right, albedo or ground reflectance. Okay. So now this is going to be an interesting topic, because now we're going to be talking about the family of the VTs, because we have different terms. When I'm saying about VTs, okay, VT family, we're going to be talking about three parts: 1, 2, and 3. So for this sunlight, we have to consider these 3 main important aspects, which is called the transmissivity, okay, double S C VT. That's why it's the family of the VTs. The other one is going to be absorptivity, okay, TVT, and the other one is going to be the reflectivity. Okay, so again, we're going to name or represent this with Greek words. This is tau, everything lowercase, and absorptivity is going to be represented by alpha, and then reflectivity is going to be by rho. And this reflectivity is the foreground reflectance. That's why it's rho G. Okay, so we have these 3 components, and there's another one. There's another one, by the way. The other one is called emissivity too. Okay, so that's the extra. We're going to put in here an extra, the extra one. So the extra one is going to be emissivity, and that's, let's put the extra emissivity in here. Emissivity. Okay, and this is represented by the word epsilon. There we go. Okay, so now that we have all these 4 parts, mainly these 3 are very important. The emissivity is very, very important too, but it's in kind of a different category. So we're going to represent how that affects to the window. Okay, so now let's, we're gonna make in here a window right here. Let's say right here. So if we have a window right here, there we go. Okay, that's a window, right? And the sun is right here. Sunlight, the sun. Okay, that's the sun. We're always gonna come to the, let's put this in a different color. Let's put as red, no, let's put as green right here. Okay. There you go. So this is 100% of energy, all right? So this is the incident radiation, okay, incident, okay? So what happens is that not all the 100% is going to be transmitted to the indoor part. So let's put that as an indoor part inside. This is going to be the indoor, okay, and that's going to be outside. This is going to be outdoor, okay, outdoor. Okay, so not everything is going to be absorbed. So in that case, what we're going to have is it's going to be transmitted some. Okay, there we go. And that's what we call transmitted. Okay, that's going to be transmitted. Okay, so from the 100%, we can say that it's been transmitted, say 78%, not all of it. And what is the rest? The rest is going to be reflected. We're going to put in here reflected. It's going to bounce, and then that's going to be reflected. Okay, so let's say that this reflected is going to be, say, 9%. Okay, 9%. Wait a minute, for what is 78 and 9%, it's not going to be 100%. So, because the other part is going to be absorbed by the window, that's going to be absorbed. Absorbed. Okay, absorbed. Absorbed by the window, and that's going to be 13%, for example. All right? Okay. So now that is how the sunlight interacts with the window. And it's very interesting that when we're talking about this representation of the VTS, properties of the sunlight, we have this rule that tau plus alpha plus rho equals to 1. In other words, transmissivity plus absorptivity plus reflectivity is going to be equal to 1, okay, or 100%. Okay, so now what we need to consider is the next part, which is called the emissivity. So what is actually the emissivity? We're going to put in here as a title like emissivity. In here, emissivity. Okay, let's put that like this. Emissivity. Okay, so for emissivity, we have this representation as epsilon, and then the definition of emissivity is actually going to be the following. This is a effectiveness, okay? So this is going to be the effectiveness, okay, of emitting, okay, emitting energy, okay, emitting energy as thermal radiation, okay, as thermal radiation, okay. So actually that is the definition that we have, okay, but however, in practice, what does that mean? Because emissivity is very important for the windows, because you're going to always see that this window is a low E, which is low emissivity. So for emissivity usually means that if this value is 0 and this value is 1, this completely absorbs the heat, which is for a black body. Okay, this is a black body, and the other one is going to be for a shiny mirror. Okay, so technically it completely reflects the energy. Okay, so in this case, let's see if we have a window. Well, let's put the window like this in green. So let's put another window right here. Okay, that's the window. Let's say that we are in winter. So no, let's put in here black. That's gonna be summer. Okay, in summer. Okay, so in summer what we have is this, what they call low E, means low emissivity. It's a coating which is very thin. It's a very thin coating. It's less even than the thickness of the human hair, and this actually impedes, this actually avoid that the sun is the thermal energy is going to get into the building. So let's put in here. So if this is the sun rays, there we go. All right, so this is going to impede that the heat goes in. So we're going to put in here solar. Okay, solar heat stays out. Okay, stays out. Why? Because it's this low emissivity, but this doesn't impede the sunlight, and sunlight is going to go in. See, sunlight goes in, no problem. Okay, so on the other hand, whenever we have like the season, let's put in here the same window, and then this is going to be actually for winter. So let's put this for winter. Okay, winter. Okay, and then again we're talking about low emissivity window, and this is a very small coating, which is in the, there we go, small coating. Okay, that's the small coating, and then actually my heat is trying to exit because outside is very cold. Say that, okay, we're going to put in here, say for example, my conditions. Outside is, say, 17 degrees Fahrenheit outdoor temperature, and inside is my indoor design temperature, which is 70 degrees Fahrenheit and 30% relative humidity. So in other words, since outside is it's colder, so the heat is going to try to get out. It's trying to get out. This is heat. However, because of this low E, not all the heat is going to get out. So, in other words, the heat is going to bounce, and some of the heat, some stays in, okay, because of this property of the low E. The same thing in summer. For example, if we have in here, say for example, outside, outside the temperature is 95 degrees Fahrenheit, and indoor we have our indoor design temperatures 75 and 50% relative humidity. Of course that the heat is going to try to get in. However, because of this low E coating, not all the thermal energy is going to go in, so it's going to bounce out. All right. So, and also there's more properties. For example, this could be in between with argon, or could be with empty air gap. So there's a lot of properties with to help this process. So that way, in summer we don't want the heat to get in. In winter we want the heat to stay in. All right. And also this, as we can see in here, we're going to put this in pink. So these properties are actually for the window, and see, this is an internal shade which is taking into account the blinds. You can always put these blinds as 45 degrees, or you can put 0, or you can, depending on the case. All right. Well, I hope you enjoyed this video. If you did, hit the like button and subscribe. All right. Thank you very much.